So I have problem 11 up on the screen. You can see that I started writing on it. Similarly, I started problem 10. I started writing on it. As I started really thinking about these problems, I think they're pretty awful. Let's just skip problem 10 and 11. I was trying to explain something that I don't know is explainable. I think they're just poor problems that I probably lifted off of some website without putting enough thought into what I was putting here. So let's skip 10 and 11. I have the problems worked out on my solutions manual, just the theory doesn't feel so good. And so I'm not even going to say a word about them. We're happy to skip those and we'll move on to something that makes more sense, something that's we're required to do. So problem 12 is disgusting. It talks, but I know I lifted this off the internet, but I like it. So it talks about the efficiency of photosynthesis in some grass in the Antarctic. And the table below lists various temperatures in degrees Celsius and how efficient the plant is in photosynthesizing. And the purpose of this research was to determine the temperature at what the photosynthesis is most efficient. So at 1.5 degrees Celsius, it's 33% efficient. At 12 degrees Celsius, the plant's 95% efficient. Boy, that looks like a great level of efficiency. So what am I supposed to do? I'm supposed to do something more scientific than just look at the data and say, well, it looks like when the temperature is 12 degrees Celsius, the plant is 95% efficient. That's its best efficiency. I'm going to try to formalize this by doing some analysis. And the first bit of my analysis is I'm going to sketch a graph of the data doing a scatter plot. Of course, we remember how to do scatter plots. I need to turn my scatter plots on because they're most definitely off. So it's second and y equals, second and y equals, hit enter on my plot, and hit enter on. Hit enter on my plot, hit enter on. Now if I hit my y equals, the stat plot is on. Let me clear any functions that I have laying around in here that are not necessary. So you need to get your calculator back to that position so we can do stat plotting. Now I'm going to enter the data. I don't feel like entering this data twice, so I'm just going to enter it once. I'm going to go stat, enter, and in my x's, I'm going to enter in list 1 the degree temperatures, and my y's are going to go in list 2. I'm going to go 1.5 degrees Celsius, 0 degrees, 2.5, just enter all the x's. Super easy to enter something wrong. I expect that on the test, so I wouldn't make a problem that has so many numbers to press. So the best I can, I'm trying to enter the data perfectly, which is, not something I consistently can do well. I think I have the data in. Once I get the data in, I can hit zoom and stat to do a plot of the data. So zoom and stat, zoom and stat, plots the data for me just fine. Boy, that doesn't look like the data is linear. Back a few sections ago, we did linear regression, and we found out that if we get an R that's 0.8 or bigger, the line's a great fit. If the R is not, if it's less than 0.8, maybe it's not such a great fit. So what am I supposed to do now? Now that I have my scatter plot that we're not going to copy on our paper, we're just going to look at our calculator. I'm going to do two kinds of regressions. I'm going to do linear regression first, find an equation of the line to fit the data as close as possible. Remember how to do linear regression? We hit the stat button, arrowed over to calc, went down to linear regression, hit enter. I liked storing the equation in y1, so I go vars, y-vars, function, enter. And then on this calculator, I go down to calculate. On this calculator, I can't show you the data because I didn't enter it, but I can show you the regression. I go stat, calc, linear regression, and then second and 1 for L1, comma, second and 2 for L2, comma, vars, y vars, equals on function, equals on y1. This calculator needs to have that pressed in, and when you do this, you get this equation, and look how bad the r is. It's negative 0.10. This is not linear at all. You look at the data, you can see it's not linear. So for part A, the linear function, I'm just going to write it with a y and an x. It's y equals negative 0.24x plus 71.35. You'll get the same answer if you have an older calculator, just the keystrokes are different. And because the r is 0.1, that's not a good fit at all. Here I graph this line, and boy, it doesn't even come close to the data. Now we're doing the new type of regression. Now I'm going to find an equation of a parabola that fits the data as close as possible by using quadratic regression. I should be similar keystrokes. Didn't even warm up on this. So let's try to do quadratic regression. Stat, calc, go down to quadratic regression, which will give me an equation of a parabola to fit the data. So stat, calc, quadratic regression. Quadratic regression looks exactly the same, so the keystrokes are going to be exactly the same. Vars, y vars, and I'm going to store this in y2 because I put the line in y1. So just so I could have both of my equations graphed simultaneously, I'm going to put that in y2. So for this, I would go second and L1, comma, second and 2 for L2, comma, vars, y vars, function, and go down to y2 so you could have each one stored separately. Now on my calculator here, I'd hit calculate. On this calculator, you just hit enter. But of course, I don't know what data I have in this calculator. It's not going to give me the right equation. It gives me an equation, but not the right equation. So the equation here, rounded to 2 decimals, the quadratic equation is y equals to negative 0.26. The a goes in front of the x squared, so negative 0.26x squared plus, rounded to 2 decimals, 7.41x plus, rounded to 2 decimals, 40.49. So that's the equation. This r squared, it doesn't give me an r, it gives me an r squared. And in a parabola, they say if it's over 0.9, it's an excellent fit. This is pretty close to 0.9. It's a better fit than the line at 0.1. So I'm thinking the graph that's a parabola, the regression that's a parabola is going to be a better fit because the line was way off. And for parabolic regression or quadratic regression, this r squared is a measure of the fit. And if the closer to 0.9 it is, or over 0.9, it's a good fit. As it's straying away from 0.9, it's not such a good fit. So if I hit graph, there's the line, it's a horrible fit, and there's the parabola. It's a pretty decent fit. I can see already if I'm using the parabola for estimating, it's not going to estimate as high. I have some points above the parabola that, for what it's worth, when I do my estimations using the parabola, I'm only going to get points on the parabola, and let me get into this and talk about that in a second. But there's everything for this. I made a scatter plot. I found my equations. Which equation looks better? I'd say the quadratic looks a lot better because of the 0.1 on the linear regression. That's no good. And this was close to 0.9. That's good. I graphed everything. I don't want you to do this anywhere but on your calculator. It's just too tedious. And so now I'm asked to find, so I made my scatter plot on my calculator, found quadratic and linear regression using essentially the same keystrokes. The quadratic equation looked better. It had an r that was really good, r squared that was really good. The linear had an r that was awful. The quadratic regression is better. Graph these on my calculator. One measly question. determine the optimal temperature. The optimal temperatures are x's, and the percent efficiency is the y's. The optimal temperature is going to be where you have it's going to be the vertex of the parabola. So the optimal temperature is the x coordinate of the vertex of the parabola, because each point, the x's are the temperature and the y's are the efficiency. And I'm trying to find the optimal temperature, and you can tell that the optimal temperature, because the parabola opens upside down, it's the maximum efficiency which occurs at the vertex of the parabola. So for the optimal temperature, I'm going to use the negative b over 2a formula using the numbers from my quadratic equation, where the a is negative 0.26 rounded to 2 decimals. The b is 7.41 rounded to 2 decimals. So the optimal temperature is going to be negative 7.41 over 2 times negative 0.26. This calculator would rock on this. Let me just go second quit to get back to the main screen. Math, bounce over to fraction and hit enter, and do negative 7.41 divided by 2 times negative 0.26, and it gives me 14.25 degrees Celsius for the optimal temperature. On my other calculator, I would do this. I'd go negative 7.41 divided by parentheses 2 times negative 0.26. Just don't use a parentheses for the times, might make the denominator easier to follow. For what it's worth, regardless of how I press the buttons, the optimal temperature is the only thing I need to find here. And the optimal temperature, according to this parabola, is 14.25 degrees Celsius. I think that's all I'm going to say. I could maybe say some more, but it makes sense that somewhere between there, the optimal, somewhere in this region between 10 and 15 would be the optimal temperature, and I'm just going to trust the algebra here. One more problem, and maybe we'll just call this the end. Let's do 13 together. It's the last regression, and it's a regression that I sometimes put on a test. And look how few data points I put on, because I wanted to make this easy and not so clunky in terms of button pressing. So a baseball player hits a low line drive. Really, his ball's going to do something like that. It's going to go up and go down. And the following data represents the height of the ball at different times. At 1 second, it's 13 feet. At 2 seconds, it's 19 feet. At 5 seconds, it's 13 feet. Make a scatter plot of the data. And of course, the window that you pick is going to maybe exaggerate how high it looks, or if it looks like a line drive, that doesn't matter. So let me make a scatter plot of the data by hitting my stat button, hitting enter on edit, works the same on all of our calculators. Go up to the top of my list, hit clear and enter, top of my list, and hit clear and enter. In list 1, put the times, which are 1 second, 2 seconds, and 5 seconds. In list 2, put the heights, which are 13 feet, 19 feet, and 13 feet. Have my data in. I'm going to make my scatter plot only in my calculator world by hitting my zoom button and going down to option 9 that says stat. There's my scatter plot. Now I'm going to use the graphing calculator to find a linear regression and a quadratic regression. So on this calculator, to do the linear regression, I go stat, calc, linear regression, and list 1, list 2, store this in y1, so vars, y-vars, function y1, have it calculate. So the linear regression, I'm going to do h's and t's. The height is negative 0.46 times the time in seconds plus 16.23. So I'm sneaky. Rather than doing y, which really doesn't have much meaning, equals negative 0.46x plus 16.23, I noticed that the x's were times and the h's were height, and I got used to doing times for t and heights for h. Both of these are okay. This is not very good. Look at the r is negative 0.27. Not a very good fit. So let's do the quadratic regression now. And I made this be a perfect fit to make the numbers nice. So stat, calc, quadratic regression, enter, list 1 for the x's, list 2 for the y's. I'm going to store this in y2 by going vars, yvars, function in y2, and then tell my calculator to calculate. And it gives me perfect. I made this perfect fit. That's when you only do 3 points, you can make it as nice as you want. Technically, this should be negative 2x squared plus 12x plus 3. I'm going to change this to the height as negative 2t squared plus 12t plus 3. R squared is a measure of how good the fit is, and a 1 means it's perfect, a perfect fit. It goes through the points perfectly. So I made it go through the points perfectly. And when we see our graph right now, you'll see that the line, it's not ridiculous, but it's nowhere as good as the parabola. I made the parabola flat out go through the points perfectly. Look how it doesn't miss the points by at all. So the parabola is definitely better. So done with the first two parts. I made my scatter plot. I used my calculator to find a linear regression and a quadratic regression. Wrote these down, rounded to 2 decimals when it was necessary. The quadratic for part C is definitely better. If I could actually spell it right now. By a lot. The r on the line wasn't any good, but the r squared on the parabola was awesome. Part D says make a scatter plot. Don't do it on your calculator. Just only do it on your calculator. Don't do it by hand. So see my calculator. And now I want to find the maximum height. I don't know what the maximum height is, but it comes in components. And I can't get the maximum height without knowing the time. The vertex has 2 components. The vertex has the time for the maximum height as its x component, and it has its maximum height in feet for the y component. So this is asking me to use this equation to find the maximum height. I can't get the maximum height without knowing the time, so I'm going to get the time for the maximum height first. And we've done this a few times already in this section. I'm going to use the negative b over 2a formula to get the time for the maximum height, where the a is the number in front of the squared term, which is negative 2. The b is the number in front of the first power term, which is 12. So this is going to be negative from the formula, 12 for the b, over 2, and then negative 2 for the a. This is going to be negative 12 over negative 4. That's going to be at 3 seconds. I get to the maximum height. How do I get the maximum height? Just like we've done before, plug the time into the equation for t. So the max height is going to be the height equals negative 2 times 3 squared plus 12 times 3 plus 3. Do this from my main screen. Second and quit and do negative 2 parentheses 3 squared plus 12 parentheses 3 plus 3. And that gives me 21 feet for my maximum height. So the answer to part E, which I took a couple steps to get, the maximum height is 21 feet. That's all I want to do in this section. If I put a quadratic regression on the test, it's always this baseball player problem. I don't think I actually put a quadratic regression on the test. I put a linear regression, at least not on the practice test. I actually haven't written the test yet. I've only written the practice tests. But when I create the test, I open up the practice test. Let me get my calculator so it's not going to mess me up. Turn in the stat plots off. by hitting the y equals button, arrow up to the stat plot, and hit enter, arrow down and make sure the stat plot is off. If your stat plot is blacked out, it's probably going to mess you up. So up to the stat plot and hit enter, shuts it off. Might as well clear anything out that I have in here because it's not going to help me later on. And I'm going to do back to zoom standard. So zoom and standard to get my calculator ready for just some generic situation that I might be presented with the next time I go to use my calculator. If I leave my calculator with the plot on, it could cause me havoc. If I leave my calculator with a zoom stat window, it might mess you up too. So we'll call this the end of section 4.4, the end of the chapter, other than we just need to get through the practice test.